So hello all and welcome back to the TFK Deep Learning series, and this is episode 3.1 where we'll be trying to understand the logistic regression, and we'll also trying to understand the gradient descent. And this is basically like the simplest way to understand neural network, because logistic regression can be seen as a neural network. All the functionalities such as doing the summation or applying activation function as we do neural network is same as here. So let's get started with logistic regression. So here we'll be looking what is it and the concept of activation function. Then we'll look into the loss function and cost function. Then the learning algorithm, which obviously is a stochastic gradient descent. And then we'll also try to touch the forward propagation and back propagation, because this is actually a concept of neural network, but you can easily understand even with logistic regression. So before we go, let's have a recap of the previous episode 2. So it there we discussed about linear regression, and if you haven't or watched, then you can go and have a look at that. So linear regression is basically predicting a real value. So example, considering a given temperature and water consumption in number of ounces. So you can train a model such that given any new value of temperature, you can predict how many consumption of water how many ounces of water will be consumed. Similarly, predicting the house prices, it's a problem of linear regression where we are predicting a real value, that's the price of the house. Then also predicting the location of the detected object, such as this position. This also is a problem of linear regression. So basically you will have data like this shown here, and you have to find the best fit line, a linear regression model which best fits such that the error among the line and the different point is the minimal, so that whenever any new value is given, suppose new value of x, you can directly predict the new value of y. Okay, so you can have that was simple linear regression where we have just one input variable. We can also have more than one input variable. So the case here, we are predicting the price of the house, and the input is the size in the bedroom. Here we can learn a linear regression plane which best fits this data, such that given any new data, we can predict the output of that new input data. So this is a whole picture of how the gradient descent can be applied to linear regression, and a linear regression model can be learned. So yeah, so basically this is the example where we have three inputs. We define some initial weights, and then we compare the predicted value with the actual value, and then we compute the error, and then with gradient descent we reduce this error such that we get the best value of this w's. So we'll discuss this again in this logistic regression, but still you can go and have a look at the previous episode 2.1. And then we implemented linear regression in TensorFlow and Keras. So in TensorFlow, you have to define the placeholders for your input variable x and y. Then you have to define variables for your weight and biases, and then you define the model, and then you define the loss function, and then you define the optimizer, and then you define a session. You run everything in a session, and then you optimize your values. Okay, so this is already implemented in episode 2.2, and then we see in episode 2.3 about how you can implement all this with just few lines of code in Keras. So Keras is pretty easy, as you can see. So yeah, enough of that. Let's get started with this episode. So what is logistic regression? So logistic regression is one of the most popular machine learning algorithm for binary classification, and logistic regression is a supervised learning algorithm, and it can be considered as a simple neural network. So you can see the diagram here. We'll have an input, we'll have a summation, we'll apply activation function, we'll get an output. So let's understand step by step. So first, I said logistic regression is a binary classifier. So binary classifier means classifying a given input or categorizing a given input in two classes. So example is here. So suppose you have a image of your retina, so you can classify it as a normal retina or a diabetic retina. So this is a binary classifier. Another example, which will even code it out, is a given marks of students in two exams, or you need to predict whether they passed, or they get admitted, or they failed, they didn't get admitted. So 0 will be they failed, and 1 will be they passed. So this also is a binary classifier. And I said it's a supervised learning. So, you'll be knowing supervised learning means we'll have the input and we'll also know the output. So the label of the input. So assume the task of car prediction or car detection. So the images will be given and we'll also know the output that these are cars, and then this input, and we'll also know the output that this is not a car. And then once the model is trained, we'll give a new data and then we'll ask it to predict whether it's a car or it's not a car. So basically, it's a supervised learning problem. So basically, for any classifier, there should be a decision unit which takes the decision of classifying the given input in a category A or category B. Okay, so in our brain, in human body, the decision unit is our brain, and in case of neural network or logistic regression, the decision unit will look something like this, such as this node, where there will be inputs coming to it, and this will make some, apply some functions and then give an output. Okay, so let's see. But before that, let me just give you a visual representation of what is the difference between this should be logistic linear regression and logistic regression. So in case of linear regression, this both are supervised learning problem. So in case of linear regression problem, we'll have the input and we have the output. Say we have the population and we have the price. The goal during the training or during the learning phase will be to learn a linear regression line, the straight line or the best fit line, such that it has minimum error from all these points. And this learned best fit line is the linear regression model. And once it is learned, given any new data, say in between this, so we can easily, knowing its parameter like equation of line y equal to mx plus c, by knowing m and c, we can, predict the new output. So this is the linear regression of learning this new line. Whereas in case of logistic regression, this is also a supervised learning problem where we know the two categories. So this data belong to category circle or category A, and this data belong to category cross or category B. The goal here is to learn a decision boundary between these two categories like this. So it's basically learning a classifier or a boundary between the different classes, such that like during training it will try to learn these boundaries, and finally when the model is trained, this classifier is learned. So given any new data, it will see if this new data falls in this side, then we can say that it belongs to class A, or if new data falls on this side, we can say it belongs to class B. So that's the a difference that you should keep in mind, just from understanding point of view. Okay, so let's get to logistic regression. So just consider example, daily example that you may be experiencing it. Assume you have to make a decision of whether you want to go to office or you want to work from home. So there can be number of inputs that you can consider while making decisions. Okay, and those inputs you will be weighting them differently depending on your thought process, and that is your decision unit. That decision unit may vary from person to person. Say for example, weather. So weather is really important to you, so you may give more weight to that weather. Suppose 0.8 if I am considering 1 as the highest and 0 as the least. Suppose boss, you are quite brave, you're not scared of your boss, so you'll give less weightage to your boss, maybe 0.1. And then you give weightage to your work, like you really have some important meetings and all, then you can give some weight like 0.3. And then based on those weights, you will combine these inputs with the weights, and then you'll make a final decision based on your threshold or your thinking that you want to go to office or not. The same thing is done in the logistic regression, but here the decision unit is the activation function, which we'll look into it. So as I said, the decision unit is the activation function. In case of logistic regression, it is the sigmoid, but there are a number of this decision units or activation functions, such as sigmoid, 10H, linear function, rectified linear unit, and leaky ReLU. So all this 1, 2, 3, and 4 are non-linear activation function, whereas this one is a linear activation function. So in sigmoid, whatever the input is, the output will be bounded between 0 and 1. It will be squashed between 0 and 1. In case of 10H, whatever the input, the output will be bounded between -1 to 1. In case of linear, the output will be same as the input. In case of ReLU or rectified linear unit, it is most commonly used in the neural networks. Any negative value will be 0, and any value greater than 0 will be the same value. So it will be a linear function above 0. And in case of leaky ReLU, it is a varied version of ReLU where anything above 0 is linear, but anything below 0 or negative value is not 0, but there is a small value attached to it, a small 0.01 or something. Okay, so let's look into the sigmoid function or the logistic function, because that's what is used in logistic regression. So sigmoid function is any input, it will be bounded between 0 and 1. So you see, this is the mathematical formula of it. So given any x, the output is 1 by 1 plus e minus x. Okay, so yeah, let's see an example of it. So suppose x is 6 here, and you take exponent of 6, and then the sigmoid of 6 comes to 0.99. So if any value is greater, much greater than 0, the output will be close to 1, and if it is going negative, the output will be close to minus, oh sorry, it will be close to 0. Okay, so consider the example of x equal to minus 6 somewhere here. So you compute the sigmoid with this formula and you will get 0.002, very close to 0. And if x is 0, if it's 0, then the sigmoid comes out to be 1.5. Okay, so you can see exponential of any value is always a positive number. So why we get between 0 and 1? So exponential of any value is always a positive number, and any number divided by the number plus 1 will be less than 1. Okay. So logistic regression now can be considered as a structure of single artificial neuron, because this unit that you see on this very slide is the basic unit of any neural network, either convolution neural network or LSTM, recurrent neural network, or whatever network you consider. This is the basic unit, and this is a logistic regression where you will have these features or the input, and this will be weighted individually, and then we'll compute the weighted sum, like w1 into x1 plus w2 into x2 plus w3 into x3, and then we add a bias term, and then we compute z, and z is passed through this function, activation function. So in case of logistic, it's sigmoid, and in case of other neural network, it can be other things. So yeah, but keep this image in mind. So you will have these unknown parameters w1, w2, w3, and b, and then w1, w2, w3 can be called as weights, and it can the number of weights will be equal to the number of features and inputs you have, and b is called bias. So weights we understand, right, that we are weighting different inputs, but what is the role of bias here? Okay, the b term. So let's have a look at this. So bias is actually the threshold at which the neurons or the decision units fires or take decisions. Okay, so consider this picture here. So you can see this is a step function. So you can see here, if x is greater than 0, y is equal to 1. If x is less than 0, you can see y is equal to 0. However, let's add some bias to it. Let's add a bias of b. Okay, so this is a bias of b terms that we are adding. Now what role does this play? Now it has changed the threshold value at which the output, which the neurons will be, or the decision will be outputting the values. So now when x is greater than this b value, then the y is 1, and when x is less than b value, y is equal to 0. So now if you shift this b value on the other side, we can get again the 0 threshold, but with the addition of this minus b term. So now if you take this b this side, so x minus b greater than 0, so y will be 1, x minus b less than 0, y equal to 1. Sorry, this will be y equal to 0. I'm sorry. Okay, so yeah, so a bias value allows you to shift the activation function to the left or right, which may be critical for successful learning. So there may be some functions which need this threshold, which will fire after, not at 0 but after some b value. So this bias helps in that, and bias is a parameters that need to be learned. Okay, so we saw, like last time, we are shifting the threshold to the right. What if we want to shift the threshold to the left? So let's see example of this. So now you are shifting the threshold to the left by a minus b term. So here, so now instead of like the same equation holded before, but now when x is greater than minus b, this value, then y is equal to 1, and when x is less than minus b means this side on the left side y is equal to 0. Then we can shift this threshold or the bias term that we added on the left side so that we get a threshold at 0. Okay, so you see in the previous slide we shifted it to the right, in this slide we shifted to the left, but it doesn't matter. What's important is this line. A bias will allow to shift the activation function to left or right, okay, which may be critical for successful learning. So it will shift this activation function so that it fires a different threshold. So this is what we are computing as z as w1 x1 w2 x2 w3 x3 plus b. So where this x is this x1 x2 x3 and will multiply with weights, and this bias is this term that you can see here, and the role is here as I explained in this slide. Okay, so I hope the bias term is clear to you now. Now, so this is another visual of showing you the role of bias term. So you can see here we are changing different weight values. So by changing the weight values, the steepness of the curve changes. Okay, but still the threshold is not changing. So assume if you want to have a zero value at 2. Okay, so suppose this is the 2, here will not get output of sigmoid is 0 because it's in the positive side. But what if we want it? What is if then network or the logistic regression is trying to learn some function from the input which requires this property? So you can, in case of this, the bias comes in picture, where suppose this was the zero bias line. So now if you add a bias of 5 here, if you add a bias of 5 here, now if you see at 2 we'll get a value of, sorry, 2 will be here, so at 2 you will get a value close to 0. Okay, so instead of, in case of here we're not getting 0 at 2, but here we can get it just by shifting this function or shifting the threshold with the help of the bias term. Okay, so that's the role of bias term. So yeah, that's the same thing I'm talking here. This picture, like the bias enables moving the activation threshold along the x-axis. When the bias is negative, the movement is met to the right side because it goes on the other side, it adds it. When the bias is positive, the movement is met to the left side. Conclusion is that biased neuron should learn even such input vectors that non-biased neuron is not able to learn. So you are able to figure it out that bias can be important property, and that's why it is learned. Okay, so another example you can see here is by comparing it with the equation of line, where there's y equal to mx plus c is the intercept. So if c was 0, the line would have passed through 0, but as c is 1 here, the line is shifted to 1 here. Okay, so yeah, that's one more. Okay, so let's summarize this. Not summarize, let's look at the big picture. So logistic regression can be considered as a structure of artificial neuron. It will have features, and all the features will be weighted. So it will have basically these unknown parameters w1, w2, w3 and b. These w's are called weights and b can be called as bias, and then we'll do a weighted sum of all these features along with the weights, w1 x1 plus w2 x2. Okay, here is a plus, should be a plus, w3 into x3 plus b. So the goal of logistic regression is to learn this w and b so that the predicted value is a good chance of being 1. So basically, since it's a binary classifier, we are predicting the probability of getting class 1, because probability of getting class 0 will be 1 minus that. So in general we can say that the ultimate goal is to learn w and b so that the predicted value is a good estimate of the actual value. Okay, so let's consider an example of this example where we have scores from 2 exams, and its final result, whether they got admitted or not.
So let's solve this problem with logistic regression. So this is our problem set where we have scores in two different exams, and we also have its result of whether the student was admitted or not. And our goal is to learn some model like this. So this A is the predicted value by the model, and X will be the input. X is this one, and yeah, we need to predict A, what its output was. So we have to learn W and B. So in this case, we have two two input variables, so our model will be looking something like this. A, that is a predicted output, is equal to w1 into x1 plus w2 into x2 plus a bias term. Okay, so let's see in this respective, let's consider the first example, 3478. But initially we don't know what W1 and W2 is. We need to learn this. So what we'll do is initially we'll choose some random value of W1, W2. So we have chosen W1, this one, W2, this one, and B, this one. So this is all random value. And then based on this random value, we are going to compute the prediction or the output by the model. So first you have to compute the, okay, so it has to be actually, this is Z, and this has to be sigmoid of, sorry, this has to be sigmoid of this term. Okay, so you see, so this is Z is a weighted sum. So x1 into w1 plus x2 into w2, you get a Z, and then this is passed through activation function. Here is the sigmoid activation function to compute the final predicted output. Okay, so this gives the probability of what is the chance that the student is getting admitted, or that he belongs to class 1. So you'll get this output 0.786. It's a very high probability, but as you can see, this is not correct. Actually, this is wrong. So how will we know that our model is doing well, or these parameters are actually a good value? Okay, so we need to have some comparison, parameters. That's where supervised learning comes in picture. As I told you, we already know what's its actual class is, or what its actual output is, and we know what model has predicted. We know how much wrong the model is. So what we can do is we can use this actual value and compare with the predicted value, and whatever differences or error which we have, that error we are going to feed it back, so that these parameters, they correct themselves to a good value. Okay, so yeah, that's the fundamental here. What's going to take place, not here in any learning stuff, in any learning algorithm. So in order to, what do you say, in order to know, there should be a function which computes how much wrong the model is doing. So that function is called loss or error function. And this loss or error function can be computed as such. So like but before that, let's assume that you have like number of examples. So consider the examples x1 y1 x2 y2 xm ym, where x1 is the input and y is the true output. So our goal is to create a model which predicts the output a, such that this a should be very close to y. Okay, so our predicted value should be very close to the true value. That's our goal. And in order to measure it or achieve this, we compute a loss or error function. The simplest way we can think of is the squared error function, that we simply subtract this predicted value from the actual value. Okay, and since this was just for one example, but we'll have, m examples. So the goal is to, reduce the error over all the examples. So that will be mean square error, where we compute loss over all the example and compute average loss, and try to reduce this average loss so that it gets generalized for all the inputs. Okay, however, if it was a linear regression where the goal is just to predict a real number or output value, it's fine. But in case of logistic regression, we are predicting the probabilities of predicting that category. It's not just a real number. The cost function or the error function is not going to be convex, and this will cause problem for our optimizer to learn the best value of, w and b. Okay, so let's see what I mean by it. So actually this is called a convex function, and this is called a non-convex function. Same you can see in the curve here. So convex function means it will have a very smooth curve with just one minima value. So we can easily, if now you will see when I explain gradient descent, we can easily chose the value here, which is the place of minimum loss or minimum error, and we can know that we have the best value. Whereas if we are having non-convex cost function, there is chance that our model may get confused and get stuck here, thinking that this is the minimum value, and just settle down that this is the best value, where in fact the best value was here. So there will be lot of local minimas where the model can get stuck into and give us a wrong solution. So we cannot use the mean square error function or mean square cost function as a error function for logistic regression. For logistic regression, we have to use something else which give us a convex function like this. So that function is the cross entropy function, and it is represented like this. So the loss or error between the predicted value a and the actual value y will be given by minus y log a plus 1 minus y log 1 minus a. So now if y is 1, it's a binary classifier, the goal will be that a is very close to 1. So the loss function simply becomes minus log a. And if y is 0, the goal will be that a is very close to 0. So the loss function a of y becomes minus log 1 minus a. Okay. And the log has a role to play here. It's a kind of computing this maximum likelihood. So what this is, so due to this log we are able to reflect even small changes in the predicted value. The small changes in the predicted values are incorporated into error function, so the model learns a better way. So what I mean is, suppose log 0.99, consider the case of 1 where a has to be close to 1. So suppose a is 0.99, this log a. So now this 0.99 will give you 0.01. Okay, and this minus log a, it becomes minus minus plus. So you see the value is close to 0. That's our goal, that error should be close to 0. However, if it was 0.9, so here the error function is 0.105 and here this 0.01. So you can see the difference between these two were 0.09, and this difference due to this loss function will be reflected in this error function output, and this error function is going to be fed into the network to correct this w and b. So you can see that due to this loss function, even the small changes are incorporated in computing better values of w and b. And similarly, in case of the y equal to 0, a need to be close to 0. So the log become 1 minus a. So 1 minus close to 0 value, and you will get this loss function close to 0. So that's our goal, to get the loss function close to 0. So now this is the loss function for one example, but we have to compute the loss function for all the examples and reduce the overall error. The overall error or the overall loss function is called the cost function, which is computing the error due to each example and then summing it and then averaging it over m examples, as you can see here. Okay. So let's look into what we have discussed in one picture. So we'll have the input data x1 x2 in this case, and the output what its actual category is, whether he got admitted or not. Then the number of inputs is equal to number of input features and number of outputs is 1. So we'll not know the model parameters w and b, so we'll choose randomly w1 w2 b, and the number of w's will be equal to the number of features or input, because we have to weight each of the input. Okay, and the bias will be just one term. So what we'll do is we'll choose random value of w1 w2, we'll compute z, the weighted sum, add a bias term to it in case we want to shift the threshold, as we discussed in previous slide, and then we compute, apply a activation function to know how much, whether this neuron or this node is activated, and we'll get a predicted probability of what is the chance of predicting the class 1, or what is the chance of predicting class 0, which will be 1 minus this value. So we now are looking only in predicting class 1. So and then what we'll do is we'll compare with the actual value. So actual value was 0, but predicted value is pretty high, and then we'll compute a error. So the error we'll compute is with the loss function, and we cannot simply subtract it, because of this is a probability value and this is just a real value. It will not be giving a perfect sense of the error. So we'll go for something like this, the cross entropy, and this error or this cost function is caused due to this initial chosen value of w and w2. Now somehow we know how much error this model is predicting, or how much wrong this model is going. So this wrongness need to be fed back, okay, such that this w1 w2 gets corrected in such a way that this difference or this error between the predicted and the actual value gets reduced. Okay. So this is our ultimate goal, to correct these values with every iteration such that this error get reduces. Okay, and this error will be used as a feedback inside the model. So as I told you, we have to compute the value of w and b such that this cost function is the minimum or it's close to 0. So we can do this using an optimizer, and the most famous and most used optimizer is the gradient descent algorithm. So we'll look into that. And excuse me. So but before that, I just wanted to show this example just for you to understand how we can make analogy between equation of straight line and any learning model. So how you plot the equation of straight line is, you'll be given x, you'll be knowing y. So based on this x and y, you'll plot this line, and somehow, I'm sorry, this is not the line. So yeah, and you will plot, sorry, this line, and once the line is plotted, somehow if you are able to measure the slope m and intercept c. Once you have measured this slope m and intercept c, given any new value of x, you can use those value of m and c to predict the new value of y. So given any new value of x, which is not in the line, but by knowing this m and c, we can predict this y. The same thing can be understood as in the learning model. So given this input x and y, we can use this input x and y. In, suppose consider this as y, we'll use this input y, output y and input x to learn these parameters w and b analogous to m and c. And once we learn this w and b, or in case of multiple features, it will be w1, w2, w3, and so on, and b. So once we learn this w and b, given any new value of x, we can predict what will be the output for that new input value. Okay, so this you can keep in mind just to have analogous of how any learning algorithm works. Okay, now let's come to the, the most important algorithm. So as I told you, we have computed this cost function j. So this cost function was due to w and b, because we chose initially random value of w and b. We computed z. So z is a function of w and b, and then we computed activation function sigmoid, which is a function of z, and z again is a function of w and b. And we use this a here in the loss function, and the loss function tell us how much wrong we are doing by comparing it with the true value y. So you can see this cost function is ultimately a function of w and b, and this cost function turns out to be, if you are using this cross entropy, it turns out to be a convex function like this. So our goal is that this is the j, this is the different value of j, different value of w and b. We have to get to this value of j where the cost value is minimum, and this is obtained where we have the best value of w and b. So at this point, we can say our W and B are the best values. So our goal is to learn this W and B with this algorithm of gradient descent. Okay. So let's see how this works out. So gradient descent is pretty simple. So with any random value of W, we'll compute a J. So now we are going to compute the gradient of J, or this loss or the cost function. And we are going to use that gradient. We are going to move opposite to that gradient. Okay. So suppose this is the gradient here. We'll always try to move downhill or try to move opposite to it, so that we reach, the minimum value. Suppose if our cost was here, you would have computed gradient, and we'll be trying to move opposite to it. Okay, in this case, trying to move towards the positive side, but ultimately we are moving downhill. Hmm? So you can see here, for example, if your cost was here, our goal will be to move downhill step by step. So over different iterations, we'll be doing this till we reach the, final, the least value of g, where which is obtained by the best value of this w. Okay, so that's why the name gradient descent, because we compute the gradient, and we subtract those. We subtract, or subtraction means moving in opposite direction. We move opposite direction of that gradient towards downhill to get the, better and better value of your parameters w and b. Okay, so when before I formulate the mathematical, equation of gradient descent, first understand what gradient is. So you will be knowing that gradient is something inclined, or it's basically a slope, and it can be defined as measuring of increase or decrease in the magnitude of a property, in our case the cost function, observed in passing from one moment, or one point, or one moment to another. In our case is passing from one value of w to another value of w, or one value of b to another value of b. So first, let's understand this slope concept. So there are two figures here. In the first case, actually slope or gradient is computes the change in the output with respect to change in input. So suppose we have a x1 input and we have a y1. Now we chose a new value of x2 and we get a new value of y2. Now this gradient will compute how much the change is induced in y when there was a change in the x dx. Okay, so we give it by dy by dx, change in y with respect to change in x, and this can simply be computed by, y2, new value of y, minus y1, old value of y, divided by new value of x minus old value of x. And at this point we'll get a positive gradient, because y2 is greater than y1, x2 is greater than x1. But consider this scenario. Here again, computing gradient is same. y2 minus y1 by x2 minus x1. But here you will see the y2 value is smaller than y1. Okay, so we will be getting a negative gradient at this side of the graph. So this concept we are going to exploit to understand the gradient descent algorithm.
So here let's take an example. Let's say we have a cost function j, which is a function just of w and not w1, w2, and b. Just to understand, let's consider one dimension only, or just a function of one variable, and assume we chose a random value of w, which gives us a cost function j somewhere here. Okay. So now we know this is not a good value. We have to reach somewhere here. So here we are going to apply gradient descent algorithm. So what's that is? So we are going to compute the gradient. So gradient is the change in y with change in j with respect to w, and you know, as in the previous slide I showed you, that at this side the slope is going to be positive or greater than 0. So we have to move in the opposite side. Okay, so how we can move in opposite side is by subtracting. We have to move somewhere this side, so we have to get some smaller value of w, so we have to subtract some values from this w. Okay, and how much the value to subtract is given by this gradient descent, and this arrow, as you can see here, is the alpha or the learning rate. So we know which direction to move, but we don't know how much to move, how much of this gradient to take into consideration to subtract at each iteration. Okay, so this we cannot directly subtract because we don't know whether we have to take a big step, because you will see what's the role of this alpha learning rate later. But there should be a step function, or step in the sense how much big step to take, whether this we will take step of this arrow or a longer arrow or whatsoever. So this is given by alpha. So we know that gradient is positive, we have to move opposite direction downhill this side, so we can simply subtract it. So new value of w will be computed over first iteration is w old value, this one, minus alpha, how much step to take, into what is the value, or that is given by this gradient, the gradient of w with gradient of j with respect to w. Okay, so we'll take this step and then we'll compute the new value of w here, so now at this w, then we'll get this value of j here. This is the value of j. Now what we'll do is we are going to repeat this step again and again. Now again we'll compute this gradient dj by dw. Again it is this side, so it will be greater than 0. So we are going to again subtract this value here and get a new value of w here and corresponding new value of j. So we are going to keep on doing this, till we reach somewhere here where the gradient will not be greater than 0. The gradient will be close to 0 because there is no slope here. So here, by that we can know that we have reached the best value of cost function j, where the j is very close to 0, and that is reached by the best value of parameter w. So we can know our model now has learned the best parameter w. Okay, so this is with this example, but considering our problem, so a is what, w1 x1 plus w2 x2 plus b. So we are going to repeat this for all the parameters, not just for one parameter. So for computing w1 will be w1 minus alpha, the dj, the cost function is a function of w1, w2 and b with respect to w1. Then again w2 will be w2 minus alpha, the gradient with respect to w2, and for b will be subtracting the b from the gradient computed with respect to b db. Okay, so this how gradient descent this is the mathematics of the gradient descent. So we'll keep on repeating this formula again and again till we reach the best value of w. Okay, and now we can say that we got the best value of w and w2b. Now consider another example. Suppose we choose random value of w somewhere on the negative side. Suppose it was randomly -5 or minus something, and we got a cost function here. Now again we'll compute a gradient, and as I showed you here, the gradient is going to be less than 0 or negative. So since the gradient is negative, the goal of gradient descent is always to move towards opposite direction, so this side. Okay, so now that algorithm which I showed you will inherently consider that, because this is negative and we have to move towards the positive side, but the formula doesn't change, will keep same, w minus alpha into gradient. But since this gradient is negative, so internally these things will minus will become plus, and the new value of w will be greater than old value of w because of addition of these terms, and this happens internally. The logic remains same, that we have to move towards the opposite direction, that we always subtract, But since the gradient is negative here, the new value adds up, and then we get a new value of W, which is going downhill towards the right side or towards the positive side. So you can see, and we are going to repeat this again and again like the previous. So we'll compute the gradient, and then we'll apply this formula to get the new value of W, and we'll keep on doing this till we get the best value of W here. So you can see, if you're on the left side, internally, it gets added, so that W keeps on increasing from negative side to the positive side till we get the best value of J here. And if you're on the right side, it just gets subtracted and reaches here. It doesn't matter where you are, the goal of gradient descent is always to move up towards opposite, or it's the goal is to descend the gradient towards the steepest descent. Okay. Similarly, the formula here is W1x1 W2x2b, and we have to do this for each of the parameters, and we can then get the best value of not W but for all the parameter W1 W2b. So this is the mathematics of gradient descent. Let's see this one iteration of gradient descent update from this picture. So this is one picture taken from Andrew Ng's deep learning.ai course, and he explains it really very well. So this is a representation of my understanding of his concepts, and you can really go and watch his courses. They're really great. So let's see one gradient descent update, one full update of cycle of how the weights get updated. So we'll have this input, the x1 x2, and we'll choose random value of w1 w2b, and these are the inputs being fed here. So we'll compute z. So we'll compute z by this formula, w1x1 w2x2 plus b, and then we'll compute this a as a sigmoid of z, and then we'll compute this loss function, what is the error, or what is the how far the predicted values from true value with this loss function, this cross entropy function, by this formula. Now this loss function, that or whatever this error which is, or the wrongness the model is producing, is caused due to our chosen value of w1 w2 and b, and we have to compute this. And even the gradient descent formula is like this, that w1 minus dj by dw1, w2 equal to w2 minus alpha dj2 by dw2. So we have to compute this dl with respect to d1 dw1 dw2, but the l, you can see the loss is a function of a, not the function of w. So what we can do is first compute dl by dA. So we can simply compute dl by dA, and if you know differentiation, you will get this value. You can try it out, and this value is then somehow going to back propagate in order to compute the loss with respect to w1 w2. Okay, and this is the backward propagation in neural network. So this is exactly what happens there, but we use a back propagation algorithm to to easily compute those gradients. But this, the logic remains here. Okay, the logic remains same here. So now we know we know the gradient of loss with respect to a, change in loss with respect to change in a. Now our goal is to compute the loss with respect to dz. Okay, so dl by dz, and this can be computed by the chain rule, because dl by dz can be written as dl by dA, which we already know, and dA by dz. Now see, a is a function of z, so we can, a is 1 by 1 plus e to the power minus z, because it's a sigmoid function. So we can compute that, and we can get dl by dz. Okay, now this gradient or this error will then back propagate to these terms. Okay, w1 w2 and b. Okay, and now our goal is to compute this loss with respect to dw. So dl by dw can be again written as a chain rule as dl by dA, we know it, dl by dA, then dA by dz, which we already know, and dz by dw we can compute it because z is a function of w's. Okay, this I'm just showing for one w. For each w you have to do that. So in this way we can compute dw, which means the how much the change in w need to be caused to improve this loss, or the gradient of loss with respect to w. So this is computed like this. So ultimately dw1 will be x1 into dz. Here dw1 means dl by dw1, dw2 means dl by dw2, and db means dl by db. So these three terms are needed for gradient descent update. So once these three terms are computed by this back propagation, then we can simply do the gradient descent update for one cycle. So w1 will be w1 minus alpha dw1, w2 equal to w2 minus alpha dw2, and b equal to b minus alpha db. So now we get the new value of w1, w2 and b, and this thing will be then again forward propagate it, and then the loss will be computed, and then again we'll back propagate, compute dl by dA, compute dl by dz, then compute dl by dw, and then this keeps on repeating till we get the best value of w1 and w2. Okay, so yeah, this is one picture that you can keep in mind to understand how one cycle of gradient descent update out. So let me just go through everything once again for the last time, so that you are able to map the whole picture what is happening. So we'll have x1 x2, we'll have w1 w2, we'll compute z, then we'll compute the predicted value of, we will choose a random value of this, and we'll do a forward propagation, and then we'll get a predicted value of this, and then we'll compute a cost function j, which is this which computes how much wrong we are doing from the actual value, and this cost function will be then fed backward. Okay, this cost function will be used to feed this information backward of how much error or wrong we are doing, to compute dw1, dw2, and db, which is the change in j with respect to change in w1, change in j with respect to w2, and change in j with respect to b. So these are the gradients or the changes that need to be done for this iteration, and then we'll compute this new value of w1, w2. This is the one update. So w1 minus alpha dw1, w2 minus alpha dw2, once it's computed, and this looks in picture something like this. So this equations what you see here, one iterations that I showed you in previous slide, some in picture it will look like this. So it will be, the first value will be here. After first update we'll get a value here, then again we'll repeat this forward propagation, backward propagation, computing dw and dw2b, and then compute the next value of w, which will give next value of j, and then we'll keep on doing this till we get the best value of w and b. Okay, so this is a whole picture of how logistic regression works. And as you can see, how much step to take, we know in which direction to move, but how much step to take is also important. So you can see if learning rate is very large, the algorithm or the gradient algorithm will overshoot, it will never converge here. And on the other side, if the learning rate is very slow, and if there may be, suppose there are some small local minima, then there is a chance that it may get stuck in somewhere here. And also the number of time and number of iteration it will take, it's very big. Okay, this is another animation which shows that. So descending with a step coefficient of 0.05 and 0.05. So here the learning rate is large, it keeps on jittering, and it never settles down, or it takes a large time to settle down, where it moves slowly and it settles down. Here the learning rate is less, and here the learning rate is more. So this is one from the Stanford course. You say we have to choose a learning rate very wisely, because learning rate plays a very important role in learning. And yeah, so this is very high learning rate, this is low learning rate, this high learning rate, and this one is the good learning rate. So this is the curve which shows the loss reduces as we keep on iterating. And if our learning rate is good, then it will iterate very nicely, like the smooth down curve. However, it's very high, it may overshoot, or it may not converge to the best value of your loss. This is another contour plot showing the same thing. And yeah, this is another contour plot showing the same thing. If the gradient, if the step is too high, then it will it will jitter, and then it will finally settle down to this. This all are showing you the gradient descent algorithm, different in different visualization. Then so till now we discussed about the gradient descent algorithm as an optimizer, but there are other optimizers like SGD with momentum, or SGD with accelerated momentum energy, or the ADA-GRAD, the ADA delta RMS prop ADAM, which are better than SGD, especially in terms of neural network and deep learning algorithms. But the logic remains same of how you are updating the weights and the biases. So we are obviously descending down towards the downhill, and then computing and then updating the weights and biases. However, the speed may vary, these advanced algorithms will be much faster than the SGD, but yeah, the concept remains same. So discuss this here.
So there can be a variant of gradient descent algorithm that we just say, based on the amount of data that are used to do one update of the parameters, weights and biases. So there is the best gradient descent or the vanilla gradient descent, where for every update we need to pass the entire training set. So for every iteration t equal to 1 to number of iterations will pass the input data, compute its loss, and then we average the loss to compute the cost. And this overall cost function, which is average over the entire training set, is then used to do the update. However, since we have to pass the entire training data set, it may for every update it may take longer time, especially if we have a larger data set. So there is this stochastic gradient descent where we do update after passing every examples. So here we for t equal to number of iterations, for I equal to 1 to number of input data, we'll pass one data, we'll compute the cost or the loss function, and then we'll use this to update the weights and the biases. So this is much faster than the batch gradient descent, but its accuracy will be little bad than this one, because here we are averaging the error over entire training set, and here we are not doing that. So also this will be jittering a lot. You will see the loss curve when it goes down, it will be jittering a lot because the error will change for every example as it is not averaged. The best one, which is something in between the batch gradient descent and the stochastic gradient descent, is the mini batch gradient descent. And but when you like coding in TensorFlow or Keras, you will see that people although use the mini batch gradient descent, but they will use the name as stochastic gradient descent. So when you see that, that actually means this mini batch gradient descent only. So hardly anybody uses this one. So this is in between this. So suppose if you have 100 examples, then you choose a batch size. It's a parameter hyperparameter that you need to choose. So suppose I'm choosing a 10, so I can have 10 batches. So for t equal to 1 to number of iterations, for I equal to 1 to number of batches, so the cost function will be computed over by taking average over 10 samples, or whatever the batch size is, and that batched average cost function will be used to do the update. So it will be something between this and this. So you can see visually, so this is one graph for the batch gradient descent. As you can see, this curve is really smooth, very nicely descends down to the global optima. Whereas in case of the stochastic gradient descent, you can see that due to update after every example, it is jittering too much. Like it's and also it's very close to the minima, but it's not exactly going to this final value. And this is more clear from here. This is the batch gradient descent. It gradually goes down to the minima value, and this is a stochastic gradient descent, which jitters a lot, and even when it is close to this area where the minimum value, it may still jitter. So one solution will be to reduce the learning rate or the anneal the learning rate in this region. So this is another curve showing the same thing. So this is also going down, the loss is reducing, but still no, it's jittering a lot because of the frequent update after every example. So this curve shows a batch gradient descent, and this box shows the stochastic gradient descent, which is jittering too much, and this is a mini batch, which is something in between both. So this is a slide from Sebastian Ruder, who's you can see in case of the batch gradient descent, the accuracy is good because we are not taking the average, we're taking the error average over the entire training set, but the update speed will be slow because for every update we need to use the entire training data set or entire input data set. Its memory usage will be high as it needs to use the entire data set, input data set. Whereas in case of the stochastic gradient descent, its accuracy is good if we are using annealing, so it will converge to the minima value or close to it. Its update speed is high because update takes place after using every single input data. Its memory is low, just uses one sample. Whereas in case of mini batch, this accuracy is good. Its update speed is mediums, in between slow and high, as it's updating after a batch of input, and its memory usage is also medium, as using a batch of input to update the weights and the biases. So these are three different types of the gradient descent. So pretty much that's all from this episode. So we saw what logistic regression is, then we saw the activation function, which here is sigmoid, then we saw the loss function and the cost function, which was cross entropy and why we use cross entropy, and then we saw the stochastic gradient descent or the gradation descent algorithm and how we can use it to update the weights, and then we understood it in terms of forward propagation and back propagation, like how we forward pass and get the loss, and then how you feed back the gradient and compute the you know uh, gradient of loss with respect to weights to update in the gradient descent. So that's all for now, and tune into the next episode where we'll see how we can implement the logistic regression in TensorFlow, and we'll be taking the problem of whether a student got admitted or not based on his or her marks into exams. So yeah, let's see how we can implement this in TensorFlow. And if you like the video, then hit the like button. If you have some queries, you can comment below, you can subscribe. And if you want to support me, you can support me on Patreon and PayPal. The links of the same will be given below. So till then, keep learning and keep exploring neurons. Bye.